Welcome to all in the webinar series of SAR data processing. In this last webinar, we will see some aspects of the applications of SAR. In today's webinar, we will see the concept of the SAR interferometry. So before going to the SAR interferometry, we will discuss about what is interferometry. So interferometry is a technique for combining the coherent measurement. As we know, the SAR is a coherent device. Okay, so that feature of the SAR we will use for the SAR interferometry concepts. So essentially looks as the difference in the phase between two different coherent measurements and deduces the distance information from this. Okay, so in the interferometry, basically we talk about the phase. Basically, the SAR measures both amplitude and phase. By having the information of the phase, we will see how different application can be used. So first application of using the phase is the SAR interferometry. Okay, and another application is the SAR polarimetry. Okay, so in this webinar series, we will see the aspect of the SAR interferometry. The SAR interferometry needs at least 2 radars or radar imaging from 2 different places. Okay, so normally the interferometry deals with the combining the coherent measurements and it will take the phase. So interferometry depends on the fact that we are using the waves. Waves means in the SAR we have the electromagnetic wave. So we will talk about the electric field associated with the electromagnetic wave. Okay, because electromagnetic waves are a function of both electric field and the magnetic field. But magnetic field can be derived from the electric field from the difference law that can be derived. Okay, so we will basically talk about the electric fields. Okay, so two waves can interact to have the brighter light. So we can say that is have the constructive interference. Okay, when they have the same phase. Okay, and when they are out of phase, then we have the darker radiation patterns, which we call the destructive interference. Okay, so when two coherent waves superimpose each other, then we have two phenomena. One is the constructive interference and second is the destructive interference. Okay, so this is the waves. When they are superimposed, then if the phase of these two waves will be same, then we have the constructive interference. When they have out of phase, then we have the destructive interference. So in your 10th class, you have studied the concept of the Young double slit experiment. So that is telling the concept of the interferometry. So the scientist Thomas Young first demonstrated the interference in the light waves from the two sources in 1801. So if this is a light source and this light source is passing through two slits. Okay, so these are two slits and these two sources, the light waves are superimposed each other. Then it has been seen on the screen that the appearance of the fringes. Okay, so and the phenomena of the interference will happen, and we have the constructive interference and we have the destructive interference. So we can see here there are two slits, S1 and S2. This is S1 and S2, two slits are there. Then the waves emerging from the slits originate from the same wavefront and therefore are always in the same phase. Okay. So two waves can interact to give the bright light, means they have the brighter waves, means they have the brighter fringes, and where they have the destructive interference, there we have the darker fringes. So this is the pattern we will see in the young double slit experiment. Okay, so there we are seeing the different fringes in the screen. So we have seen different concepts of the dam generation using the remote sensing. Okay, so it has both techniques, means we have the imaging techniques and we have the non-imaging techniques. Okay, so here we can say like the formulation 3D save from technique from X. Okay, that X can be anything. So X can be a photogrammetry technique, it can be an interferometry technique, it can be a radargrammetry technique. So as we have seen in the photogrammetry, we have two stereo pairs. From the stereo pairs, we compute the parallax, and from the parallax, we can derive the height of the features on the Earth's surface. Okay, same the concept of the photogrammetry. If we use the pair of SAR images, then it is called the radargrammetry. In the radargrammetry, it uses the same concept of the photogrammetry, means we have to calculate the parallax, and from the parallax, we have to derive the height of the Earth's surfaces. But the interferometry is little bit different. In both photogrammetry and radargrammetry, we will use the amplitude images. Means from the amplitude images, we will find out the parallax. Parallax is basically is the image matching algorithm we are using. So by the formulation of the image matching, we will find out the corresponding image point in the amplitude image. But in the interferometry, we will use both amplitude and phase in the derivation of the 3D height from the surface. Okay, so these are three concepts: photogrammetry, interferometry, and radargrammetry. Okay, and the second techniques are the non-imaging techniques. In the non-imaging techniques, we are using like LiDAR. Okay, so LiDAR, like ISAT is the satellite, space-borne satellite we are using. So basically, it is non-imaging, means it is giving a profile of the 3D points. So we are getting the point cloud data, and another is sonar. Okay, so these are some of the technique of the dam generation using imaging and non-imaging techniques. So basically in this webinar, we will concentrate on the interferometry, and in the interferometry, basically we will see how to derive the dam from the ISRO pair. So what is the SAR interferometry, or in short we can say ISRO? So the SAR interferometry is a imaging technique in which two or more SAR acquisitions are required over the same area by the same SAR and almost the same imaging geometry, exploiting the phase differences. So basically, like interference normal young double slit experiment, we have seen two sources of light. So here, what are the two sources of SAR sensors are act, because it is an active sensor, so it will emit the electromagnetic radiations. So that electromagnetic radiations or waves, it will see the same area. Okay, so these electromagnetic waves will superimpose each other, and the interference will happen between them. Okay, so from this interference, means from the interference we have using the phase, and that phase is some have the relation with the range as well as the target height. Okay, so from that phase we will derive the terrain height of the different features of the Earth surface. So here we can see, if this is the source of light and we have the two slits are there, then we have two source of waves are there. So when it is a normal screen is there, and so they will form the interference, and dark fringes will dark and bright fringes will form on the screen like this, because it is the screen is flat. Okay, suppose if it is not flat, then it has some deformation. Okay, then these two sources of electromagnetic wave, when it will form the interference, then we can see how the fringes will form due to the deformation of this surface. Okay, so we can see this is, if it is a flat surface, then we can see the perfectly bright and dark fringes are there. But if there is a deformation in the surface, then we can see there is some changes in the fringes. Okay, so that fringes changes in the fringes will give some of the information about the terrain surface. Okay, so if we subtract from this and this, we can get the information of the terrain surface. Okay, so this is the sum of the INSAR principle, means why we are using this concept in deriving the terrain features over the ground, because of using the formula of the interference. So before going to the interference, first we will discuss about the INSAR geometry. And INSAR geometry, we will see basically the baseline. So what is the baseline? Baseline is defined as the separation between the two antenna position, either mounted on an aircraft or realized by two ideally parallel satellite orbits. Okay, so if you can see, this is two SARs, A1 and A2. So then what is the separation between these antenna positions? So this B is the baseline. Okay, so if these are two sensors, then the distance between these two sensors is called the baseline. So its length is called the B, and its orientation is given by the angle alpha. Okay, so this baseline can be divided into two components. We can divide this baseline either in two ways. First, like horizontal and vertical components. Like if this is the baseline, then we can derive, and we can see this is along the horizontal, what is its component BH, and what is its component BV. So this, if this is the alpha angle, so we can say BV is equals to sine alpha and BH is equals to cos alpha. Okay, from this formulation. And another way we can decompose, or we can divide the components like the perpendicular baseline and the parallel baseline. Okay, so what is that? That projection on the slant planes. Okay, so if this is the B, and we can project on the slant planes. Okay, so this is the slant planes. Then we can component is like this is B parallel, which is parallel to the slant range, and another component is B perpendicular, which is perpendicular to the slant range. So what is the projection on slant range? The projection perpendicular to the slant range is called the perpendicular baseline, and the projection parallel to the slant range is called the parallel baseline. Okay, so if this is the configuration of the INSAR, then we have this baseline, B perpendicular and B parallel. Okay, so basically what we will use in our geometrical calculation in the INSAR, we will use this B perpendicular. This B perpendicular is mostly used for any calculation. Okay, so basically for any processing of INSAR, we have to find first baseline and different components, B perpendicular, B parallel, and B horizontal, and B vertical. And out of these, B perpendicular is mostly used while calculation. So this is the INSAR geometry, means if this is the SAR1 and this is SAR2, so this is the slant range. Okay, this is the slant range, and this is the R dash, means R plus delta R. So if this is the distance of delta R, okay, so this is R plus delta R. So this length is R dash, which is called the R plus delta R, or we can say this is R1 and this is R2. Then R1 is equals to R and R2 is equals to R plus delta R. Okay, and this is the baseline. Alpha is the that orientation angle, and this is the perpendicular, means perpendicular baseline, B perpendicular. This is the height of the sensor H, and if this is the terrain, then it is the height of the terrain from the mean sea level or through the ellipsoid. Okay, so this delta R is called the path difference. Okay, this is the path difference. So satellite height is H, terrain height is small h, and look, this is the look angle. When this R is making with some of the nadir, this is a nadir line. So this angle is called the look angle. So what is the relationship between this H and H, capital H means with the terrain height and the satellite height, we have H is equals to H minus R cos theta. So from this geometry we can formulate, and we can see the formula is H is equals to H minus R cos theta. Okay, and you can see these waves are this master and slave, means one of the sensor is called master and second slave is called the slave, and this is the wave propagation. Okay, so this have some of the phase delay. We have to calculate the phase delay of these two SAR sensors, and from there we will use some calculation to derive the height. So how the two SAR interferometry look like? So these are the two pairs. So one is called the master and second is called the slave. So this is the image of the Uluru, Australia, and captured by the TerraSAR X satellite. So in the SAR image, basically what we have the amplitude and we have the phase. Okay, so this is the amplitude image. You can see an amplitude is given by the real square plus imaginary square and the whole square root, and the phase is given by the tan inverse of imaginary by real. Okay, so if we have the SAR SLC product, means in my previous webinar we have seen different products are there, means we have the raw product, we have the SLC product, we have the ground range product, we have the ellipsoid corrected products. But for the SAR interferometry, which product we have to use? We have to use the SLC image, because the SLC image has it is a processed image and it has the information of phase. Okay, so basically every satellite will provide the SLC image, and then we have to start our processing from the SLC image. So the SLC image contains the both component, real and imaginary. From the real and imaginary we have to derive the amplitude and phase. Amplitude is given by this formula and phase is given by this formula. Okay, so this information we will get from the SAR image. Okay, so what is the phase? So phase is a measure of how far the wave has traveled. Means if this is a wave, then how much far it has traveled. So what is the relationship between the phase and the distance travel is given by the phi is equals to 2 pi d by lambda. Okay, so d is the distance it is traveled. Okay, so if d is equals to 2r, why we are taking 2r? Means we are using the two SAR sensors and they are different two SAR sensors. Okay, so we are using this 2r, but if the SAR sensors have means both transmitter and receiver, means interferometry is done by the single platform, then we have only single r. But in case of two different orbits we are using, then we have the 2r. If the SAR interferometry is done by two different orbits, then we will use 2r configuration. If it is used by single orbit, then we have to use the simply r. So if we are putting d is equals to 2r, then the formula is phi is equals to 4 pi by lambda r. So this is the relationship which we will have, means the slant range with the phase. So actually the phase information in a single SAR image has not any application. Means if you have a single image, then we have amplitude and phase both, but the phase has not any application if it is single. But if we have two SAR images, if we can view the from another position, means if we will see the same area with some other position or some other orbit, then differences in phase between two SAR images tell about the differences in the distances. Okay, then the formula is given by delta phi is equals to minus 4 pi by lambda into delta r. Delta r is given by r1 minus r2, means this is this slant range and this is the second slant range. Then the difference between two slant ranges is given by the delta r. Then we know the basic formula is phi is equals to 4 pi by lambda into the path difference. So this is the path difference. This is the value is delta r. So this is the path difference. So we have studied in our 11th and 12th class also the path difference and the phase difference. The same formula we are using between the phase difference and path difference. It is 4 pi by lambda into the path difference. Path difference is given by the delta r. So how the different configurations of the SAR system. Okay, so we have like single pass interferometry and repeat pass or repeat track interferometry. So for the single pass interferometry, both antennas are located on the same platform, which is ideal for measuring the topography. Means we have the both antennas, SAR antennas in the same platform. Like in our SRTM mission, means we have the SRTM dam, we have the shuttle mission of that one. Then that in that case, we have both the antennas are on the same platform. Okay, so that is called a single pass interferometry. So but we are using our most of our processing the SRTM dam, which is of 90-meter and 30-meter. So both that is derived through the interferometry technique. Okay, and which is the mode? It is the single pass interferometry. Okay, so what is the repeat pass or repeat track interferometry? The single antenna SAR system which acquire the images of the same scene from slightly displaced track orbits. Okay, means it will acquire the same scene with different two orbits, or the displacement between the two orbits will be very small. Okay, so that is called the repeat track interferometry. Means we are seeing the image with the two different orbits, but in the single pass interferometry we have the orbit and we have this because we have two antennas on the same platform with the same orbit, we are able to see the scene. But in the repeat pass we are using two different orbits for seeing the image. And in terms of data acquisition, there is differentiation like across track interferometry and along track interferometry. So if the SAR antenna is displaced in the across track direction, okay, so that is called the across track interferometry. So in the SAR image, we have two things. One is across track, which is called the range, and second is the along track, which is called the azimuth. So if the antennas are displaced in the direction of the range, means in the direction of the across track, so it is called the across track interferometry. If the displacement of the two antennas is along the azimuth or along track, that is called the along track interferometry. So both have different application. Means if we have to derive the digital elevation dam or we have to say the surface deformation, then we have to use the across track interferometry, because in the SAR image the range is contributed towards the height. Okay, so that if we have to derive the height information, then we have to use the across track interferometry. And if we want to have to measure the velocity of targets moving towards or away from the radar, then we have to use the along track interferometry, because in the azimuth we have the SAR is moving, so we have to find the relative speeds of the different targets. Then we have to have the along track interferometry configuration. So basically in this webinar we have I am taking about the derivation of the dam. Then we will more concentrated on the across track interferometry, and it is of like repeat pass interferometry. Means if and the sensor is observing a scene from two different orbits, then it is a repeat pass interferometry. And because we are interested on the dam derivation, then it is called the across track interferometry. Okay. So what is that? Repeat pass interferometry for dam generation. So based on two image acquisition of the same scene from slightly displaced orbits of the satellites. Okay, so means it is the repeat pass track. Means it have two orbits with some displaced orbits, and the phase information of two image data file is then superimposed. The two phase values at each pixels are subtracted, leading to an intro program that records only the differences in phase between the two original images. The phase differences can be related to the altitude variation at each position in the swath and enable the production of the digital elevation model. Means in this repeat pass interferometry, we have two SARs in which has the displays in the across track direction, and they will see the same scene. So we have two images. So we have two phase images, Then these two phase images, we have to find out the phase differences, and from the phase differences we have to find out the height of the terrain. Okay, so that is the normal procedure of deriving the digital elevation model. Okay, so what are the basic steps? Like process data to SLC images. Okay, then register the two images to 1/10th of the pixel. So first we have to take two SLC images. If directly product is given like SLC images, then we will start from there. If the data is like of the raw data, if then we have to process the data. Means we have to process means we have to use the range Doppler algorithm and different algorithm to focus the data to make it level 1 or SLC images. Okay, so if the data is already available in the SLC image, then we will directly take the SLC image. Then we have to register these two images. Then we have to find the conjugate multiply to form the interferogram. Then we have to remove the flat earth fringes. We have to measure the coherence. We have to unwrap the phase. Then we have to estimate some geometry parameters like baseline. Then we have to convert the unwrapped phase to the height. Okay, so these are some of the steps for the dam generation. So this is a flow chart. Means if we have this complex SAR1 image and this is complex SAR2 image, then we have to do the find and code registration. Then we have to do the interferogram generation by multiplying this image with the complex conjugate of this one. Then we have to do flattening, then phase unwrapping, then phase to height conversion, and then we have to geocode the image. Okay, so this is the SAR processing chain. Okay, so now I will tell one by one each method. The first is the co-registration. So why the co-registration is required? Because the SAR interferometric pair are not registered due to the SAR geometry, orbit parameters, and timing information. Okay, so means we have some orbit parameters are there, or we have some timing mismatch of some seconds or some means some microseconds, or the SAR geometry. So that SAR interferometric pair are not registered. So first we have to register. So the SAR interferometry requires pixel-to-pixel match between the common features in the SAR image pairs. Because we are taking like have to find out the phase difference between the each of the pixel. So first, if we have to subtracting the phase of each of the pixel, then first we have to register the pixel level. Okay, so thus co-register and the alignments of the SAR image from two antennas is an essential step. Okay, so it has both a shift in both direction, means in the range direction and in the azimuth direction. Okay, so we have the shift in both directions. So a range direction is called the X direction and the azimuth direction is called the Y direction. So the first image is called the master image and the second image is called as the slave image, which is to be registered with respect to the master image. Okay, so we have two images, then we can call one as the master image because that is the base image. Then the slave image we have to register with respect to the master image. So this is the co-registration step. So if we can see, this is the master image and this is the slave image. So you can see this is the how they are not registered properly. Some shift is there. So if this shift is there, then we cannot form the interferogram because each pixels are not registered. So first step is to register the both images up to the subpixel accuracy. Okay. So the normal optical image matching traditionally needs only 1 or 2 pixel accuracy, which is called coarse registration for the SAR images. The correlation window is used to search for offsets between the master and the slave image. Okay, so basically how the co-registration is applied, it is using the basically upon the cross correlation. After this pixel level co-registration, an interferogram may be generated, but it is not adequate for the interferometric process. The phase co-registration accuracy must be higher, so a sub-pixel level co-registration must be performed. Okay. It means in the optical case, we have up to the pixel level accuracy. Means we have the two optical images. Then with the help of the cross correlation, what we have to do, we have to find one of the translation, means what is the shift in the x and what is the shift in the y. So that shift can be used for the full global registration. So that is called the coarse registration. Means with a single number we are registering the whole image. Okay, but in our SAR, what we have to do, we have to register each of the pixel. So that pixel matching we have to do very accurately and up to the level of the subpixel. So the subpixel to subpixel match, which is called the fine co-registration, which will give the high precision co-registered in SAR images. Okay, so what we will do, we will have the same correlation concept, but we have different windows are there, and we will find different points. Means in the SAR image, we will find different points in the SAR image. Then we have to fit a polynomial and we have to transform the image. Okay, so that first or second order polynomial transformation equations are preferred to find the conjugate matching points. The most commonly used method for correlation is to compute the complex cross correlation function between the two SAR images. Okay, so in the fine co-registration, what we will do, in different windows, we will find the match points, and that match points we will fit out transformation function, and we will register these two images. Unlike in the optical, where we have to find only single number and we are registering the image. So this is, we can see the after co-registration, this is the master image and this is the registered image. Okay, so here you can see it is registered up to the level of the subpixel. Okay, so this is the co-registration. The first step is the co-registration. And after that means, if once the intro program is generated, then what we have to do, we have to form the intro program. So how to form the intro program? What we will do, we have the relation. Means if we have two SAR1 and SAR2, then we have two phases. Means the formula is 4 pi by lambda R1 and 4 pi by lambda R2. These are two phases. And we have two SAR images. Like y1 is equals to amplitude of exponential of z j51 and y2 exponential of j52. So that is the amplitude of first image. This is amplitude of second image, and this is phase of first image, and this is phase of second image. So these two equations represent two SAR images. Then what we will do, we will multiply these two equations with the complex conjugate. Okay, so then we will y into complex conjugate of the y2. Then what we will get, y1, y2 and exponential of j51 minus y2. This is called the phase difference. Now this phase difference is, we can relate with this formula and we can derive the height from it. Okay, so first we have to do this intro program. Intro program, what is this one? This is the phase difference we have to form. So what is the intro program generation? For generating an intro program, two co-register SAR images covering the same areas multiplied in a complex fashion. Means we have to do the multiplication with respect to the complex conjugate. Then we will get the interference pattern, which is called the fringes. And because the phase is it is in the range of minus pi to pi or 0 to 2 pi. So the phase will be lies between either in 0 to 2 pi or minus pi to pi. The intro program shows the differences in phase. Okay, so if we will display the intro program, then what it will show, it is show the differences in phase. These phase differences is the results of the path length differences that can be caused by the elevation differences. Okay, so this is the important point. In the phase difference is the result of the path length difference that is caused by the elevation differences. So because we have different terrain elevation, then due to these elevation we have different slant range. So that different slant range, we have different path differences, and their path differences is related to the phase difference. We know the formula, and like phase difference is equals to 4 pi by lambda into the path difference. That path difference will be coming from the equation of the slant range, and that slant range, due to the terrain variation, we have different terrain values of range, and that ranges will have the different path lengths. So that phase difference image will show actually the different terrain undulates. Okay, hence we can use the intro program to derive the accurate elevation map, monitoring the small motions and detect tiny deformation. Okay, so how to calculate the phase interferometry? Subtract the phase of the slave from that of the master. So that is called the phase interferogram. And just what we have to do, we have to multiply these two images with the complex conjugate, then the images will have the difference of the phases, and that differences of the phases is called the interferogram. So that is the interferogram. Means if we have shown the difference of two phases, then how it will look. This is the interferogram of the first. Means directly what we are doing the complex conjugate, and we are displaying the phase part of the product of the complex conjugate. Okay. So while doing the INSAR calculation, INSAR processing, first we have to see the coherence also. So that coherence, what is the coherence? Is the measure of correlation of the phase information of the two corresponding signals and varies in the range of 0 to 1. So we will from that multiplication we will also derive this coherence map also. That coherence map is given by the S1 into S2 star and divided by S1 star and S2 star, when star is given by the complex conjugate. So first we will see the how much coherence is the image. Okay, if there is the brighter areas indicate the regions of high coherence, and the dark areas represent the low coherence regions. Okay, if the image is looking brighter and the value is greater than 0.4, then we can say the image is the good coherence. Okay, so for doing first doing the anything in the INSAR processing, we have to see the first the intro program, and we have to first see the coherence. If coherence is good, then we will do the INSAR processing. Okay, so in doing the dam derivation from the INSAR, first we have to check the we have to form the intro program, then we have to calculate the coherence, how much coherence is there. If coherence is good, then we will go ahead for our INSAR processing. So the SAR interferometric phase is actually the combination of different phases. Okay, so first is called the flat earth phase, second is called the topographic phase, and third is the displacement phase, and that is the atmospheric phase, and that is the noise phase. So we will mostly consider in case of our dam derivation that flat earth surface, because I am saying the we have the phases for different terrain structure, but one common phase is due to the slant range. Means one common slant range difference is there. So that is called the flat earth surface. Means what is the distance of the satellite to the flat earth. So that is the common phase. So that phase we have to subtract it. So that is called the flat earth phase. Second is the topographic phase that we are deriving. Means that is of the undulations of the surface. And third is the if any phase is there due to the displacement of the target features. That is caused also used for the DNSAR, differential interferometry technique. So basically these two we will use flat and elevation for our dam derivation. So for, the first step is the interferogram generation. Then we will check the coherency. If the coherency is good, then we will do the interferogram flattening. What is that? The interferometric phase variation can be split into two contributions. Okay, so first is the phase variation proportional to the altitude difference Q between the point targets. Means if the terrain is there, and if Q is the terrain differences, then first is the phase difference will introduce due to the terrain undulates, and second is the phase variation proportional to the slant range displacement S of the point targets. So one that is slant range, which is common to all targets. That is called the, and the phase is also introduced by that slant range. So that slant range phase is called the flat earth surface, and that is called the 4 pi by B perpendicular by lambda of n theta r, where B perpendicular baseline, theta is the look angle, r is the slant range. So this slant, due to this slant range, one common flat earth phase is formed for every target point target. So that flat earth phase we have to subtract from the interferogram. So we have the flat earth surface phase we have to subtract it from the interferogram. It will generate a phase map which is proportional to the relative trend. Okay, so this is the flattened interferogram. So here you can see, you can compare. This is the without earth phase removal, and this is the flattened interferogram. This is the flattened, and here this is the earth phase removal. You can see these common fringes parallel. This is our flat earth fringes. Okay, so these flat earth fringes we have to remove. So that is removed by subtracting the earth phase, and that is flat earth surface, which is introduced to us due to the common R, one slant range. So that we have to remove. So after removing that flat earth, this is the flattened interferogram. Okay, so what we have done three processes. First, we have done the co-registration. Then we have formed the interferogram. Then from the interferogram, what we have done, we have subtract the earth phase. So after subtracting the earth phase, which is called the flattened interferogram. After that, one important concept is the phase unwrapping. Okay, so what is phase unwrapping? So an interferogram contains the phase information which is directly related to the topography. What I am saying, like interferogram, because in the interferogram it will represent the phase differences. That phase differences basically it is coming through to the terrain variation. Okay. So if the slant range of two different terrain targets differ by an integer number of the SAR wavelength, they will appear with the same phase on the interferogram. Okay, means if the two targets, if the slant range difference is a integer multiple of the wavelength, then they have the same phase. Okay, so every information in the interferogram is a modulo of 2 pi, means the phase lies between 0 to 2 pi. Okay, so if this is the actual terrain profile, so due to the property of the aliasing, then the phase is wrapped in between 0 to 2 pi, means if the phase is greater than 2 pi also, but due to the property of this one, it is always lies between the 0 to 2 pi. So this is the unwrapped phase we can call, means from the actual elevation profile, the phase is not actual phase we are getting, but the wrapped phase, which is the wrap around the values of 0 to 2 pi. Okay, so means if we are having greater than 2 pi values, but in the SAR interferogram, it will wrap in from the values of 0 to 2 pi. Because of the property of this one, the slant ranges of two different terrain targets differ by an integer multiple of SAR wavelength, then they will appear with the same phase on the interferogram. So this is actual elevation profile, and this is the wrap phase. So what we have to do, we have to unwrap it, and we have to find out the unwrapped phase. So again, we have to find as this elevation profile, then we have to get a unwrapped phase in like this one. Okay, so that is called the phase unwrapping. So what is we have to do? The aim of the phase unwrapping is to recover the integer multiple of cycles and is to be added to the wrapped phase so that the unambiguous phase value can be obtained for each image pixel. Okay, so if this is the wrapped phase, and this is the unwrapped phase, and phi is the wrapped phase, then from this wrapped phase, what we have to multiply the n integer of 2 pi so that we can find the value of the unwrapped phase. Okay, so and this algorithm we will use like branch cut method and fringe line detection for phase unwrapping. Okay, so what we will do, if we have to add the different integer multiple of 2 pi, and we have to see how the new phase will come. So in this way we have to find the new phase, which is called the unwrapped phase from the SAR interferogram. So after the phase unwrapping, you can see how the interferogram look like. So this is the unwrapped phase. So you can compare. So this is the unwrapped phase. This is the wrapped phase. Okay, so you can see all this this is fringes in the interferogram because it is wrapped. So this is coming as a fringes in this interferogram. So after the phase unwrapping, all that fringes, small fringes, which is actually wrapped around 0 to 2 pi, has been gone, and that is unwrapped, and it will give the true terrain variations. Okay, so this is the variation which is given by the true terrain surfaces. Okay, so that is the unwrapped phase. So what we have done 4 processes. Means we have co-registered the image. Then what we have done, we have done the complex conjugate multiplication and formed the interferogram. After the interferogram, because it is containing some of the earth phase also, so what we have find out, we have subtract the earth phase. After the earth phase, it is called the flattened interferogram. After this flattened interferogram, what we have done, we have the done the phase unwrapping, because the phase because the terrain surface in the phase differences image have are wrapped around 0 to 2 pi values. All the values are wrapped from the values of 0 to 2 pi. So that values, what we have done, we have unwrapped it, and we are doing the actual values of the phase. Okay, so here all the values are wrapped. It is not representing the original values. Then we have unwrapped the phase, and that is the actual values of the phase. Okay, so that is called the unwrapped phase. So that is the unwrapped phase interferogram. So now from the interferogram, what we have to do, we have to derive the terrain height features. Okay, so from the this geometry, we have the law of cosines like this one. Then we have the formula. If we can consider like R is very greater than B, means R is slant range and this baseline is very small as compared to this R, and R is very much greater than delta R. So this approximation we can do, and this formula we can do by approximation. Then delta R we will get like minus B sine theta minus alpha. Theta is the look angle, alpha is the orientation angle of the baseline. Then we can differentiate with respect to theta. Okay, then we have B cos theta minus alpha. Then what we will have the relation which I have shown in the first slide, H is equals to H minus R cos theta. This relation we will get. Then what we will do, we will find some of the calculation of with respect to differentiation with respect to delta R. Okay, and we will find the after doing some of the calculation, which is we will get like dH is the R sine theta B perpendicular lambda by 4 pi into d phi. So this d phi, what is this d phi? This is the interferogram, and that is the interferogram is unwrapped interferogram. So from that one, and using this relation, okay, we can derive some of the geometric parameters like look angle, we can derive slant range already given, and perpendicular baseline. That perpendicular baseline we have to find out. Then this equation can be used to derive dH. Okay, because d phi already known, d phi is the interferogram difference in the phases, and if we multiply with this one, we will get the height of the terrain. So if we use this formula, then we will see this is the dam, relative dam. Okay. After that, what we have to do, we have to do the geocoding of the dam. Now, what is the geocoding of the dam? Because you can see this image is not in the our normal map projection. It is in the slant range geometry only. Because I am saying like interferometry, what we will do? We will have to do in the uh, slant range plane only. So everything up to till now we are doing in the slant range image. So this image in the slant range plane only. So what we have to do? We have to do the geocoding of the dam. Okay. So how to do means in the last webinar what I have seen, I have told you the geocoding algorithm in which I have told you about the geocoded ellipsoid corrected and geocode terrain correction for the SAR image. So that two algorithms is used for the geocoding of the SAR image. So same algorithm is used for the geocoding of this dam. Okay, because this dam is there and we have the one and that dam derived with respect to the master of the slave image, then that image can be used and that orbit parameters can be used for geocoding of the dam. So how we can see digital elevation model derived using the interferometry is in the slant range plane. Then geocoding needed for the derived dam using the range Doppler geolocation algorithm. So as I told in the last lecture, we have range Doppler geolocation algorithm which have three equations. Means we have the range equation, we have Doppler equation, and we have the earth equation. And if you want to do the ortho rectification of the dam, then we should have one reference dam also. That reference dam can be of anything, of 90 meter or 30 meter, as good as good accuracy or better resolution dam we can have. That dam and that regress sensor model, which is called the range Doppler algorithm, which is used for the geocoding of the dam. Okay, so that algorithm is used for the geocoding of the dam. So how it will look? So using that concept, we have geocoded the dam. So that is the geocoded terrain corrected product of the dam using the external dam, which can be used as a SRT of 90 or 30 meter. So this dam will have same. We can look in the map projection or in the earth geometry. We can transform the our slant range dam. Okay, so our slant range dam, it is looking like this one, and after geocoding it will look like this one. So this is called the geocoding of the dam. So in measuring the topography, we have different constraints. So first is the baseline must lie within the acceptable limits. Okay, motion in the scene must be negligible. Coherence must be high enough, means coherence should be greater than 0.4. If the baseline is too small, the sensitivity to topography will be low and the phase noise may dominate. And if the baseline is too large, then phase aliasing may occur and the coherence will drop. Okay, so baseline is not like we have very much small baseline and very much large baseline, because if the baseline is too much small, then there will be the very much phase noise will be there. Okay, and if it is too large, then it is very much difficult to have the phase unwrapping. So there is a phase aliasing will be there, and it will be very much difficult for our phase unwrapping process, and also the coherence will drop. Okay, so what is the criteria? So for the baseline limit, so the sensitivity of the baseline to high changes increases with decreasing length of the baseline. So if we have the lower baseline, then the high changes variation will increase. Okay, so for better sensitivity of the high surfaces, we should have the smaller baseline. But how much small? So the interferogram with very small perpendicular baseline values like less than 30 meter are though easy to unwrap, but are almost useless due to their high sensitivity to the phase noise and atmospheric effect. So very small perpendicular baseline, which is less than 30 meter, are very much highly sensitive to the phase noise and atmospheric effects. The positive thing is it is easy to unwrap, but it will be of no use. Second is intro program with normal baseline, means it is if it is greater than 450 meter, are usually almost impossible to unwrap if no prior dam is available. Okay, so if we are doing the phase unwrapping, if we don't have any dam information, means outside dam is not there, so it is impossible to unwrap the phase if the baseline is too much higher. And also the coherence is generally small due to the high geometrical decorrelation, because due to the high baseline, means it is greater than 450, then we have geometrically more distortion will be there in two images. Okay, so there will be the generally a high coherence will be very much low, but geometrically decorrelation is very much high. Okay, so if we have the baseline greater than 450, then we don't have the best interferometry pair. The optimum perpendicular baseline should be the range between 150 meter to 300 meter. Okay, so optimum perpendicular baseline should be in between 150 meter to 300 meter. Okay, so that is the some of the criteria for choosing the baseline limit. Now I will give some of the aspects of the differential interferometry. So why differential interferometry is used? The surface change can be observed by the differential interferometry with an accuracy of the few centimeters. So differential interferometry is based on multiple observation interferometry. Means if we have two passes. Okay, so basically with the two passes we will generally derive the topography of the image. Topography of the surface. But if we have the more than two passes, then we can also have what are the displacement or surface changes with respect to the topography. Means what is the change reduction with respect to altitude, and that one we can observe if we have more than two passes. So how the relationship we have when the two observations are made from the same location in space but at different times. The interferometric phase is proportional to any change in the range of surface feature directly. So if this, and that is the relation, then rho T1 is the slant range at T1 time, and it is T2 time. Then the formula is 4 pi by lambda rho of, means rho is the slant range only of delta T. So it is can be utilized for the map surface deformation or long-term monitoring of the seismic phenomena. Now, how it can be done means if we have 3-pass repeat track, then we have two different baselines. Okay, so from there we have to find two different baselines. Then from each of the pair we will form two interferogram. Two interferogram is generated, and the subtraction of the two interferogram will give the surface relief change or deformation. Baseline should be as small as possible. Means from the 3-pass we will see two pairs. Means first interferogram between 1 and 2 pass, and second interferogram between 1 or 2, 3. Like that, two interferogram can be formed, and these difference of these two interferogram will give the deformation in the surface. Understand? So this is the geometry of the differential interferometry. So 3 passes is there. So if this is the R distance, this is R plus delta R, and this is R plus delta R2 plus delta R. Delta R is the difference in the changes in the topography. Okay. So this is the differential interferometry. So in this way, what we have to do means if we have 3 passes, pass 1, pass 2, and pass 3. Then from the pass 1 and pass 2, we will form one interferogram. Okay. And from pass 1 and pass 3, we will find another interferogram. Okay, that interferogram is called phi 1 plus change. If we subtract these two interferogram, then we will have the change map. And after that, the processing will be the same. Okay, so what we have to do, if we have the 3 passes, we will find out any of the 2 pair interferogram. 2 interferogram will be there. We have to subtract these 2 interferogram, and then we have to do same in processing, like we have to do the flattening, and then when we have to do the height to height conversion. So these, and if we will do this unwrap phase, then changes, and after that phase to height conversion, that phase to height conversion, and then geocoding. So this is the formulation of the 3-pass differential in SAR. Now, if we have only 2 pair, so in if we have only 2 pair, from that also we can do in differential interferometry, but we should have some external dam. Okay, so but in the 2-pass differential interferometry, if we have 2 passes, then we have to form interferogram with the 2 passes. So one interferogram will be generated from this one, and second interferogram is generated through pass 2, and we have the external dam. So that is called the simulated interferogram. Due to the, because we already know the deformations in the dam, because it has Z values. From that Z values, we will simulate the interferogram. So that is called the simulated interferogram, and this is from the actual pass one. If we subtract this one, because it is having the actual topography, and it is having from the image, and it is from the dam. So difference of this one will give the change map or surface deformation. Okay, so because it has some of the deformation with respect to this dam. So if we will form one interferogram between the actual image and one from the dam, and if we will subtract this one, then we will get the change map, and from there we can derive the height, and then we can form the geocoding, and then we can find the height of this one. Okay, so that is called the displacement map. We will have the 2-pass interferometry. Now, last is the along track interferometry. Means up to now we are talking about the across track interferometry. Means we are basically concentrate on the deriving the depth. So in the across track interferometry, basically we are finding the topography, or we will find out the surface deformation. But in the along track interferometry, if the 2 antennas are separated in the along track, so we can find out the velocity of different features, means like ships or ocean currents, we can find out velocity. Okay, so the formulation of that one is relatively simple. The formula is delta phi is equals to 2 pi by lambda into 2r. If 2 pi is because of the, if 2 of the antennas are located on the same platform, so 2 pi by lambda into delta r. Then 2 pi by, if we will divide by delta t, then delta r by del r by del t into delta t. Then this del r by del t is given by velocity. That is the velocity of the any moving thing. And this delta t is how we have to find out from the SAR sensor. That SAR sensor will give the velocity of satellite, and this that is the baseline in the s direction. So from that we can derive this v. V is given by delta phi lambda of v set 2 pi by dx. So that velocity can be derived. So the use of the short baseline helps detect the fast moving objects such as vehicles. The use of the long baseline is suited to show the slow movements such as CI. Okay, so it is in our application, but we want to find out the velocity. If you have to find out the velocity of the fast moving object, then the baseline should be as low as possible. But if we are using the interferometry for CI motion, then we have to use the long baseline. Okay. So this is the all about the SAR interferometry, in which we have discussed different type of SAR interferometry configuration, basic concepts, how to generate the dam from the SAR interferometry using the repeat pass across track interferometry, in which we have done the different processes like co-registration, interferogram formation, flattening the interferogram. Then we have done the phase unwrapping, then phase to height conversions. And lastly, we have done the geocoding of the interferogram. That's all in this webinar series. So in this webinar series, you have learned about how to do first from the basic concepts of the SAR images. Means how the SAR image looks like, different properties in terms of their backscatter values, and that one. In the second webinar, we have seen how to process the data with respect to the Raw data means different focusing algorithms like range Doppler algorithm, what is pulse compression, what is linear frequency modulation techniques, what is RCM correction. After forming the level 1 product, we have done the level 2 processing. The level 2 processing, what we have used the geolocation and geocoding algorithm, in which we have used different equations like range equation, Doppler equation, Earth equations. From the dam, we have derived the coded terrain corrected product, and if the average height is given, then we have derived the geocoded ellipsoid corrected product. So up to that, we have different products level like raw product, we have SLC product, we have geocoded product, we have ground range product, we have geocoded terrain product. So after that, in today's we have learned about the application of the SAR. For that, we have taken the SLC images, two SLC images of the SAR interferometry, and generated the dam using the SAR interferometry. Okay, so these are some of the concepts of the basic concepts of the SAR data processing, which includes the raw data processing, level 2 processing, and the processing of the interferometric data. Okay, you can post the questions. I will try to answer.